So the chapter is wave. First definition, a process in which energy is transferred from one point to other without shifting any material is called wave. So process in which energy is transferred from one point to other without shifting any material is called wave. So number one, mechanical wave. A wave which requires medium to transfer energy from one point to other is called mechanical wave, like waves, ripples in water, sound wave, etc. And number two is electromagnetic wave. A wave which does not require any medium to transfer energy from one point to other is called electromagnetic wave. Now, this mechanical wave is produced by disturbing the medium. When medium is disturbed, mechanical wave is produced, but the electromagnetic wave is produced by perpendicular oscillation of electric and magnetic field. For example, this is medium water. When it is disturbed with the help of the stick, so the ripples are produced, so the mechanical wave is produced by disturbing the medium. But in electromagnetic wave, we have to arrange two fields. One is the magnetic and the second, the electric field. When both oscillates up and down, left and right, this is the oscillation of the magnetic field. This is the oscillation of the electric field. Then an electromagnetic wave is produced, which must be perpendicular to the both. See, first definition of the transverse wave, a wave in which direction of vibration of particles is perpendicular to the direction of transfer of energy. So if the direction of the vibration is like this, up and down, and energy is traveling in this direction, then this is the example of the transverse wave. For example, a rope. It is fixed with wall. When this end is moved up and down, this disturbance is traveling horizontally. So energy is going in this direction and the vibration perpendicular. So this is the example of the transverse wave. Next, in this longitudinal wave, direction of vibration of particles in the medium is parallel to the direction of transfer of energy. Like this particle, molecule of the air, is moving forward and backward during compression rarefaction, and the energy is also traveling in this direction. So the next is waves in water are the transverse wave. But sound is longitudinal wave. Similarly, all electromagnetic waves are transverse wave. All electromagnetic wave are transverse wave because they are produced by the perpendicular oscillation, but mechanical wave either transverse or longitudinal. But all electromagnetic waves are transverse wave. Next, the transverse wave can be drawn like this. This is crest, this is trough, crest and trough, and so on. So this is crest, this is trough, crest, and trough. Suppose the wave is carrying energy in this direction, but all particles of the medium in the transverse wave, in the water wave, are moving up and down. So this is moving up, down. This is moving up, down, up, and down. Similarly, all particles are moving up and down in perpendicular to the direction of transfer of energy. Now, if the question is, this is number 1, this is number 2 particle, this is number 3, this is 4, this is 5, this is 6, this is 7. Draw the direction of the motion of each particle at this instant. So the simple method is, if the energy is going towards right, if the wave is propagating towards right, move your finger towards left along the wave. So I will move the finger in this direction. This is the shortcut. Then the direction of the motion of the finger, your finger is the direction of the motion of the particle. So at this 7, it is moving up, 6 moving up, 5 moving down, 4 moving down, 3 up, 2 up, 1 down. Energy is going towards right. Move your finger towards the left along the wave. Then the direction of the motion of your finger will give you the direction of the particle. But here, at this point, at this point, at the peak, the finger is neither moving up nor down. It is horizontal. It means these particles are momentarily at rest, and the later they will go to this mean position. At this instant, all particles at the peak of crest and trough are stationary. Again, suppose this is the wave. And the wave is traveling in this direction. So this particle is moving up. This particle moving up. So from this peak to this peak, all particles are moving up, but these particles are moving down. Now, this particle suppose is P. This particle is also P, is Q suppose. Now there is a similarity or similarities between P and Q. According to the rule, both are moving down. Both are moving down. Both are at the one side of this equilibrium line, and both are at the same distance from the equilibrium line. So number one, P and Q are at same side of mean position. Number two, at same distance from mean position. In short, for these two, they have same displacement from the mean position. And number three, P and Q are moving in one direction. So these points are called in phase points. So the P and Q are the in phase because they have three similarities. P and Q are at the same side of the mean position, at the same distance from the mean position, are moving in the same position. They are in phase point, but the difference is both are the part of different wave. This is the first wave and this is the second wave. So number four, the difference is both belong to two different waves. And the next, the distance between two consecutive in phase points is called wavelength. Distance between two consecutive in phase points is called wavelength, which is represented by lambda. Okay, next. After this definition, frequency is the number of waves produced per unit time, mean number of the waves produced in 1 second. So the frequency is equal to number of waves divided by time. Number has no unit, time second, second power minus 1, which is called hertz. But for one wave, time taken to complete itself, in time required by one wave to complete itself, is called period, and it is represented by capital T measured in second. So the frequency Suppose the number divided by time, number one wave, and the time taken by one wave is t. That's why frequency is 1 over t. But the original formula is total number of the waves divided by total time. And similarly, distance covered by one wave is represented by wavelength, mean the length of the one wave, according to the formula distance, speed into time. If the wave is 1, then the distance will be lambda, v times, and the time will be period. So we can write lambda divided by time period is v, or v is equal to 1 hour time periods into lambda, but 1 hour time period is frequency, so v is equal to f lambda. Now the next definition is intensity of the wave. Intensity is the rate of transfer of energy per unit area by the wave. Rate of transfer of energy per unit area by the wave. This rate of transfer of energy is called the power. So the intensity of the wave is equal to power divided by area. So the power is measured in watts, area in meter square. So the unit will be watts per meter square. And then intensity is equal to P divided by A, power divided by area, energy divided by time divided by area. But this intensity, number one, depends on the amplitude square, directly proportional to amplitude square of the wave. Number two, intensity directly proportional to frequency square, but intensity inversely proportional to distance square, which is covered by the wave. So these are three factors affecting the intensity of the wave. Is wavefront. It is an imaginary line joining all points at the front of a wave which are in phase. It is an imaginary line joining all points at the front of the wave which are in phase, and it represents crest of a wave. For example, this is wave. These are the crest. So line drawn at the crest is wavefront. So this is wavefront number one, this is two, this is three, and the distance between two consecutive crests is lambda. Hence, the distance between two consecutive wavefront line is also lambda. So distance between two consecutive wavefronts line is equal to wavelength lambda. So this wavefront number one, this is two next. So this is lambda. Now for the straight waves, wavefronts are drawn like this. These are the wavefronts, mean they are showing the crest part of the wave. But when wave is circular, so the wavefronts are also circular, and these are representing the crest portion of the wave. If the wave is transferring energy in all possible directions, then it is said to be unpolarized. If the wave is transferring energy in all possible directions, suppose this is the light, it is transferring energy in all possible directions, this is unpolarized. But when a wave is forced to transfer energy or travel only in one direction, one plane, then it is said to be polarized. So the bulb is transferring energy in all possible directions. It is unpolarized, but a laser light is transferring energy only in one direction, so this is polarized. And do remember, transverse wave can be polarized only. Longitudinal wave cannot be polarized because it travels in all possible direction, but the light is a transverse wave. It can be polarized. It travels in the form of the beam. Light is transverse wave, so it can be polarized. So sometimes light is written as monochromatic. Monochromatic mean single color light, single frequency, single wavelength, like red, blue, green. These are monochromatic lights, but the other one is polychromatic. And polychromatic mean multicolor light. And the best example for this is white light, which is the combination of the 7 color VIBGYOR. Similarly, cyan, magenta, many colored light. So it has many wavelengths and many frequencies. So monochromatic, single color light, polychromatic, many color light. And the best example is the white light because it's a combination of 7 colors.